So just wanted to bring us back to the schedule, where we are and what we have left to accomplish. So we're on week 3. I'm sorry, week 13. And so today we are covering actually chapter 8, which is solutions. And then the following week, we'll cover acids and bases. In terms of stuff left, you have a few homework assignments left. You have a little bit of lab work to do. The lab work is just going to be reading and answering questions. So that's not too bad. And you obviously have your final exam. It'll be conducted on Blackboard. In terms of what's due directly this week, your group peer review is due for your chemistry wiki. I will give you guys your comments back by the end of today, so you can look to incorporate those. And then the final draft will be due at the end of the semester. So you got a couple weeks to, poke it and prod it, make it better, and incorporate all the comments myself and your peers have given you. In terms of lab materials, just wanted to make a quick mention of that. So we hop on down to week 13, which is soluble and insoluble salts. There is the standard pre and post lab here, just the standard questions. And then there is an actual solubility work for you to turn in. So you download this little thing, you answer some questions, and you turn it in here. It gets you 3 points just for doing it. So just to show like, you're working. And there will be a corresponding one for the following week with the acids and bases work as well. So please make sure you do this. It's not like going to break the bank in terms of points, but it's basically 3 free points, and you'll know everything you need to know after today's class lecture, I should say. But we don't need to meet for lab. I'm sure you guys like that. So this is just a worksheet you can do on your own time. It is due at some point. Yeah, so it's due next Friday. So you got time to do it. But we won't meet for the lab just because we're going to talk about the things that you're going to be covering in lab in lecture. So I don't really see the point of meeting. But yeah, so that's our goal. Not a ton left to do, but I'm sure that's probably good for you guys because you probably have a bunch of things for other classes to do. So as long as you keep up with the work, everything should be okay. I also posted the grades to your second exam. I will send out a separate announcement about how I'm going to adjust the grades for the second exam and the first exam, just because the second exam also is relatively low, like the first one. So you'll know more about how your grade for your exams will be adjusted very shortly. I just have to make the decision. If you have any questions, let me know. For those of you that are not too familiar with online learning, a couple ways you can ask some questions during class. You can type it in the chat, you can raise your hand, or you could just speak. One of the 3 will get my attention. But obviously, any questions on the lecture or grading or anything like that, please feel free to reach out to me. Just a little bit of material left to cover. So, and then, we're on break, so which is nice. Alrighty, so today we're going to cover solutions, and it's an interesting class. I think the next class will be much more interesting because it has much more. Well, I think this class has a lot of real-world applications as well, but I think the pH material has a lot more real-world applications. So we've discussed this idea of a mixture before, and so we've given some terminology thus far. And so we talked about a pure substance. So it's elements, covalent compounds, and ionic compounds, right? Where a pure substance is just one thing. Like I have a brick of copper, or I have a pure cube of salt. Right? So pure substances, nothing else. However, most stuff we come into contact, whether it's biological or non-biological, is a mixture of 2 or more pure substances mixed together. And we term this as a heterogeneous mixture. And typically speaking, a heterogeneous mixture I'm sorry, we term this as a mixture, and there are two types of mixtures. The first being a heterogeneous mixture, where it does not have uniform composition throughout the sample. So picture if you have like a glass of water and you dump some salt in it, the water, dissolves some of the salt, but a lot of the salt will stay on the bottom. So it's not mixed homogeneously. Because it was mixed homogeneously, all that salt would have dissolved, and the concentration of salt would have been mixed all throughout your glass of water. So two distinct types, heterogeneous and a homogeneous mixture. One's ununiform and one is uniform. And homo, you should recognize homo meaning the same, so it means it's uniformly mixed. Hetero meaning sort of mixed, right? If you think about like hetero and homosexual, right? Hetero is male-female, homosexual is male-male or male-female, right? So kind of an easy sort of way to think about mixtures, I guess. I can't think of another instance where people use hetero and homo, commonly outside of talking about sexual orientation. But I digress. Now, a solution itself is typically homogeneous mixture that contains small particles, and liquid solutions, typically speaking, are transparent. Now, solutions themselves consist of two distinct parts. The solute, which is the substance present in the lesser amount, and the solvent is the substance present in a larger amount. Now, if we go back to our idea of dissolving salt in a glass of water, water would be the solvent, and salt would be the solute. So typically speaking, the solute in a mixture is going to be what you're trying to dissolve in your liquid. Right? You can't dissolve something in solids or gases, but you can dissolve something in a liquid. So that's what we're sort of focusing on today is liquids. Now, when we think about a solute, it's going to be in lesser concentrations as well. But again, it's typically, you think of a solute as whatever you're trying to dissolve in your liquid. So if I add sugar to water or salt to water or sugar to my coffee, right? I'm trying to dissolve that physically in my water. So the solute is going to be sugar, the solvent is going to be water or coffee or whatever liquid we're talking about. Now, we have a blanket term here, what you call an aqueous solution, and the vast majority of stuff we're going to be talking about is going to be aqueous solutions, and as its name implies, aqueous being water-based. So in an aqueous solution, water is the solvent, i.e. what is doing the dissolving and what is present in a larger amount. And so we could just sort of look at sort of this idea of a mixture. So we have air, which is two or more gases. So we have oxygen, carbon dioxide, and nitrogen, as well as water. So it's a mixture it's going to be heterogeneous in its, I'm sorry, not heterogeneous, but a mixture of multiple different gases. We have a saline solution, which is a solid dissolved in a liquid. So salt, NaCl, dissolved in water. So this would be an aqueous solution. And then we have a dental filling, which is a liquid in a solid. So in this case, it's mercury and silver, mercury being Hg and silver being Ag. So, three ways to sort of thinking about a solution, right? We're typically thinking about solutions as in, like this, an aqueous solution, but you can think of a solution in multiple shapes or forms. Now, when we're thinking about mixtures, we have a new term which is called a colloid, and that might be something that's relatively new conceptually to most of you. But a colloid is what we call a homogeneous mixture that has a larger particles, often having a opaque appearance. Now, if you've ever seen like, like for instance, like fresh squeezed like orange juice or lemonade, right? You have very large particles. A lot of it's dissolved in water, but it has an opaque overall appearance. And that's what we think about sort of as like a colloid. Colloids are typically, like larger in size. Particles that are in a colloid cannot physically be filtered from its other components, and they do not settle out. So they're not just hanging out at the bottom of your solution. And then we have a suspension, which is a heterogeneous mixture that contains large particles suspended in a liquid. And so these particles are so large that they physically cannot dissolve in a liquid, but they can be filtered away from the liquid or separated using a centrifuge. And a centrifuge is just a fancy way of spinning something very, very fast. So that's what we have. So you can think of like a suspension, like technically speaking, when you add oil to water, that's technically a suspension. But these are sort of two things, and I have a sort of like a handy table here for you. So solutions, colloids, and suspension. A solution is particle size that's very, very small, less than 1 nanometers. There's no settling, and the components cannot be separated by filtration. A colloid, which is this, and so on and so forth. So nice little handy table that summarizes basically the past 3 slides for you. Handy for exams and whatnot. So this brings us to our, I guess, our Gatorade slides, thinking about electrolytes and the converse of electrolyte, which is a non-electrolyte. Now, any substance that conducts an electrical current in water is simply called an electrolyte. It's pretty straightforward. Electricity, right? So doesn't conduct. If it conducts electricity, it's electrolyte. If it doesn't conduct electricity, then it's a non-electrolyte. So what this looks like conceptually. So salt, so just table salt, sodium chloride, NaCl, dissociates into water. So you should remember that hydrogen bonding of water will pull sodium chloride apart, causing it to dissociate. Now, once it dissociates, we have sodium positive ions and negatively charged chlorine ions, both dissolved in an aqueous solution. Now, those charges themselves, the plus and the minus, help conduct an electrical current, thus making sodium chloride an electrolyte. In contrast, pure water does not conduct an electrical current. So water molecules inherently have a neutral charge. They do not dissociate in water, right? Water isn't pulled apart by water. It's just water and water. And it simply does not conduct an electrical current. So whenever you see electricity in water, it's not the water that's physically conducting the electrical current. It's actually the electrolytes dissolved in the water. So now, a strong electrolyte dissociates completely into water and forms ions. A weak electrolyte dissociates partially in water to form some ions, leaving mostly uncharged molecules. Now, this is a sort of a nice handy table. So we have a strong electrolyte, which speciates, i.e. it breaks down into ions, so positively and negatively charged things, conducts a very strong electrical current. And some examples of this include sodium chloride, potassium hydroxide, hydrochloric acid, potassium bromide. So very, very strong electrolytes. There are weak electrolytes, including ammonia, I forget what this is off the top of my head, hydrofluoric acid. Right, so these ones are conducting electric current, much weaker than, say, a strong current, and they have molecules with fewer ions. And then finally, we have our non-electrolytes, which stay as molecules in solution. They don't conduct any electrical current and include, this would be ethanol and hydrogen peroxide. So things that physically aren't pulled apart by water. And I think one of the things that's relatively easy to sort of pick out if you're paying attention is the very strong electrolytes are, typically speaking, something positively charged bound with something negatively charged. So in the case of sodium chloride, that's an ionic compound, right? Positively charged sodium bonds with negatively charged chlorine. Potassium hydroxide here, negatively charged hydroxide, positively charged potassium. Hydrochloric acid, essentially no charge of hydrogen, negatively charged chlorine, and the same thing for KBr. So a lot of strong electrolytes you can physically just see. It's usually like a halide, i.e. like a chlorine or a bromine bound to a metal. That's sort of the easy way to see it. The other common thing we see is acids such as hydrochloric acid, sulfuric acid would be another one. You see those physically, acids are pretty common, strong electrolytes. And then things bound to hydroxides, KOH, so the hydroxide being OH. Things bound to OHs typically are strong electrolytes as well. So just some easy things to remember about what makes it. But ultimately, what's mostly important is what it physically does, right? A strong electrolyte does this, a weak one does this, and a non-electrolyte does this. So this brings us to a new math term, which we're going to call an EQ, or equivalent. And this is simply the number of moles of charge that a molecule ion contributes to a solution. It's different than it's sort of a different way to think about it, because we're talking about the number of moles of a charge, not moles of a substance, but moles of a charge. And the number of EQs per mole of an ion equals the charge of the ion itself. What does that mean? Well, if we go down to this nice little handy table here, if we have 1 mole of sodium, it's positively charged once. The equivalents are going to be 1 EQ of sodium. So you look at basically what the superscript is on your ion here. So this would be sodium +1. This would be calcium 2+. This is carbonic acid -1, and this is phosphate -3. Their corresponding EQs are simply going to be whatever that superscript is. 3 for phosphate, 1 for carbonic acid, and 2 for calcium, and 1 for sodium. So really easy, right? Conceptually easy, but you can actually do some math based around this, and so it's more simple algebra, which is good. Now, the example we're going to give is a medical example. Now, if an intravenous aqueous sodium chloride solution contains 154 MEQ, so milli equivalents per liter of sodium ions, how many MEQ of sodium is in a patient that is given 800 milliliters of a solution? So as we sort of always do these things, we identify what we know and what we want to know. So we know we have 800 milliliters, that's our starting quantity, and we have 154 millieqs per liter of sodium ions. Our desired quantity is, given this much volume, how many MEQs of sodium do we give the patient? Again, this is how much our concentration is, right? You see we have MEQ per liter, thus implying a concentration. We give them X amount of liquid. What we're trying to figure out is, in this much liquid, given this concentration, how much MEQ of sodium do we have? So we have to do some conversions first, because we have some conflicting scientific, oh my goodness, units. There we go. We have some conflicting units. We have liters and milliliters, and so we have to convert. So first thing we need to do is write out some conversion factors, as we always do. We have 1 liter is 1,000 milliliters, or there's 1,000 milliliters in 1 liters. We choose this one because we start with 800 milliliters. We want to go to liters because our original starting quantity, MEQ per liter, here is in per liter. So we have to convert one of these to liters, right? So we'll choose to convert 800 milliliters into liters here. So we'll choose this factor because milliliters here cancels milliliters here, leaving us with 800 milliliters times 1 liter over 1,000 milliliters, thus canceling milliliters, leaving us liters here, canceling the liters here. So we end up getting basically 0.8 times 154 MEQ sodium. Math tells us we cancel out liters and milliliters, leaving us simply 123 MEQ of sodium. So all we had to do really here is just do some algebra, right? Which is nice. There's no special equations, but conceptually, let's just go back, right? Our answer ended up being 123 MEQ of sodium, but we know the concentration starting was 154 MEQ per liter. So we took a small subsection of that. Thus, we only have a small amount of this 154 MEQ per liter. Exciting stuff, I know. Now, we have some general features of this term solubility. And, this is something that's actually kind of intuitive to you guys. You just probably didn't think about it. So when you are cooking or you're baking or you're putting sugar in your iced tea or your coffee or something like that, there's only so much you could put of any given solute into a solvent before it stops dissolving. And it varies depending on what compound you're looking at. Now, this brings us to this term solubility, which is the amount of a solute that can physically dissolve in a given amount of solvent. And so the units here we usually have are in grams of solute per 100 milliliters of solution. So our units end up being grams per 100 milliliters. Now, a saturated solution contains the maximum grams of solute that can physically dissolve. What does that mean? Well, if my solubility of, say, sugar in water is 100 grams per 100 milliliters, a saturated solution of that would be exactly 100 grams of sugar dissolved in 100 milliliters of water. In contrast, we have an unsaturated solution that contains less than the maximum grams of a solute that physically can dissolve. So again, if my solubility of sugar in water is 100 grams per 100 milliliters, if I have less than 100 grams of sugar dissolved in 100 milliliters of water, then I simply have a unsaturated solution. So as you push this boundary, whether it's hitting the exact amount or less or over it, you either are saturated or unsaturated. Now, if you push way over it, so if you go past, say, again, 100 grams per 100 milliliters, say we go to 300 grams per 100 milliliters, we then become what we call supersaturated. So you can oversaturate or supersaturate a solution as well. It doesn't have to just be saturated or unsaturated. But the best, and the thing that I remember, so I remember this from high school. So this is almost 15 years ago now, but we can summarize solubility as a 3-letter term, or a saying, like dissolves like. And that will do you very well to remember that going forward. It will also help you a lot in life. Like dissolves like is a really handy thing to remember when you're cooking and baking and all sorts of things. It really is, but it's an important thing for chemistry. Now, what do I mean by like dissolves like? Well, things that have similar properties will dissolve in things that also have similar properties. So if I have oil in water, you guys know that when you add oil to water, oil does not dissolve in water. Well, why is that? Oil and water have completely opposite properties. Thus, we are not satisfying this like dissolves like problem. So we have some rules we can discuss here. Most ionic and polar covalent compounds are soluble in water. And water itself is a polar solvent. So you remember water has polarity to it, right? It has a slight negative charge on the oxygen, a slight positive charge on the hydrogens. And water itself, using this, will pull apart something that is ionic, i.e. table salt. As you should recall, table salt, sodium chloride, is physically a positively charged sodium bound with a negatively charged chlorine. So like dissolves like. Ionic and polar covalent compounds are soluble in water. Now, small neutral molecules with oxygen or nitrogen atoms that can be hydrogen bound to water are also soluble. Now, the example I'll give you here is ethanol. So this is what you use for hand sanitizer. This is also what's in, like, beer and wine and all those fun things. But the presence of this OH here means there's a potential for a hydrogen bond to form between the oxygen and the hydrogen, as well as the hydrogen and the oxygen. Because of this, because there's a potential to form a hydrogen bond, ethanol is dissolvable in water. So what does that mean conceptually for you guys? Well, if you've ever drank, well, some of you are too young for this, but pretend when you're older, if you're not of if you're not of age, that you drink an alcoholic beverage. Well, it tells you, like, say 20% alcohol per volume. Well, why? What is the remaining volume? If 20% is alcohol, the remainder has to be water, right? So ethanol in this case is dissolving physically in water, right? And it does it because it has this potential to form a hydrogen bond in water. Next up, we have nonpolar compounds are soluble in nonpolar solvents. And this is like dissolves like. So we can look at octane, which is nonpolar, and shoot, I forget the name of this compound. Crap. Whatever this compound's name is, CCl4. Octane will dissolve in CCl4 because both are non-polar liquid that only exhibit our friends' London dispersal forces. So when you mix octane and CCl4 together, you get a mixture where one dissolves in the other. Excuse me. Sorry about that. It's not very often I sneeze during class, but again, nonpolar in nonpolar because like dissolves like. So conversely, if we stuck octane into water, the octane in the water would separate because octane is nonpolar, water is polar, thus they would not dissolve in one another. No matter how much of one you add, you simply won't dissolve, right? So octane is the most common hydrocarbon we combust in our gas tanks. So when you see like octane 95 on the gas, the gas when you fill up your car, if you do drive a car, of course, we're combusting octane mostly. There's some other stuff in there, but mostly octane to power our cars. So if you ever mix gasoline and water, you'll know that they separate because gas is polar. I'm sorry, non-polar. Water is polar. Like doesn't dissolve, right? There's no like dissolving like here. So, all right. So next up in our solubility train is when dissolving something in something releases more energy that is required to separate the particles, the overall process is exothermic. So in your lab before, we went on Thanksgiving break, you dissolve some calcium carbonate, calcium chloride in water. You probably noticed that the tube got a little bit hot. Why was that? Because the energy required to break the calcium chloride apart was less than the amount of energy released by breaking the calcium chloride. By dissolving the calcium chloride in water. So when that happens, when this is satisfied, the process is exothermic. Heat is released, and so you guys visualized last week that your tubes physically got warmer. You can measure with a thermometer. You could feel it with your hands, right? Because to break the bonds of calcium required only a little bit of energy, but breaking the bonds by dissolving it in water released a lot of energy, thus heating your tube. Now, the converse to that is when the separation of particles requires more energy than is released during solvation, i.e. dissolving something, the process is endothermic, thus heat is absorbed. So one of the other compounds you worked with before Thanksgiving break, you dissolved it in water, the tube got a little bit colder. Not like, ice cold, but it got a little bit colder. Why is that? Because to break those bonds, it was consuming the energy in the water, thus dropping the temperature of the water. So kind of fun, conceptually, especially, when we did it last week. So that's where we are, but we have some big rules that we'll discuss about solubility. Now, rule number one, a compound is soluble if it contains one or more of the following cations. Group 1A cations, so that's our very first column in the periodic table, lithium, sodium, potassium, cesium, and I don't remember this guy's name. So if it's got positively charged, it's going to be soluble. Ammonia, also containing a positively charged thing, also soluble. Rule 2, if a compound is soluble if it contains one of the following anions, i.e. something that's negatively charged. So group 7A are halides, chlorine, bromine, and iodine. Now, there are some exceptions to this. These will not dissolve if you are dissolving them in a salt with silver and mercury in them, as well as lead. Just as a note, that's not going to be something you're going to have to remember, but that's just a general solubility rule for halides. So our group 7A. Nitrate will also make something dissolve. Acetate, CH3, CO2 minus, and sulfate, SO2 2 minus. And sulfate will only dissolve except in the presence of salts with barium, mercury, and lead as well. So again, this last part, these last except for, you don't really need to worry about them, but I just figured I'd make mention because that's just a general rule. But what you'll notice is that there's charges here. Things with charges are readily soluble. It's a pretty consistent thing. Now, when we're thinking about this solubility, we're typically thinking about it in terms of water, right? That's mostly what we're thinking about. Now, if we had gasoline, for instance, you could not dissolve a halide in gasoline, right? Because gasoline is nonpolar. This is, charged, thus they're not going to interact with one another. So we're thinking about these solubility terms relative to water here. Okay, so now, as many of you probably sort of intuitively know from baking or cooking, solubility typically increases as temperature increases. So if you took a tablespoon of sugar and put it into freezing cold water, most of that sugar would not dissolve. However, if you took that same cup of water and you boiled it, you added sugar to it, all that sugar would then dissolve. Because as you increase temperature, you increase solubility, i.e. the amount of a given substance that you can dissolve in a defined volume of liquid. Makes intuitive sense, right? Because think about what temperature means, right? Molecules are moving faster. And think about what dissolving really is. It's just something being pulled apart, right? Salt is pulled apart in water. That's how it dissolves. So if something is being pulled apart, the probability of it being pulled apart increases as temperature increases. Because remember, temperature is just a measure of how fast things are moving. So the faster things are moving, the more probability for collisions, thus the more likely something is to be soluble. That's conceptually what's going on in terms of atoms and all that fun junk. Now, as I've sort of mentioned this term, but by dissolving a solid in a solvent at a very high temperature and allowing it to cool very slowly, we can create what's called a supersaturated solution. Now, a supersaturated solution, as I've already mentioned, contains more than the predicted maximum amount of a given solute at a given temperature. So if we can only do 100 grams per 100 mils of sugar into water, oops, oops, 100 grams of sugar into 100 milliliters of water. If I heat my water up to boiling temperature and I dissolve 500 grams of sugar into 100 milliliters of water, and I cool that down and the sugar stays all dissolved, I then have a supersaturated solution. Just as a note. Now, the other thing I'll just make mention of is that the solubility of a gas also decreases with increasing temperature. Now, conceptually, what does that look like? Well, if you think about oxygen and other gases dissolved in the global ocean, the Arctic Ocean has a lot more oxygen than the equatorial ocean, so stuff around the equator, because the equator has warmer water, thus it can dissolve less gas at higher temperatures. And why? And conceptually, why is that? Remember, gases don't have a defined volume, right? So they're just, as you increase their temperature, they're moving faster, thus they're likely to escape liquids. That's sort of how that works. So it's kind of the opposite of what we typically think for solubility. Gases kind of buck the trend. Cooler waters means you can dissolve more gas. Hotter waters mean you can dissolve less gas. So, um, you know, not a lot of practicality in terms of your average everyday life, but definitely something that matters to the ocean. So, all right. So our I guess we'd be kind of remiss if we didn't talk about a law at some point in this lecture. We typically talk about at least one law per week, but the law we're going to talk about this week is Henry's law. Now, Henry's law states the solubility of a gas in a liquid is proportional to the partial pressure of the gas above the liquid. So, what does that mean? Well, the idea is the higher the pressure, the higher the solubility of a gas in a solvent. So remember, gases have pressure. So when you blow up a balloon, right, and that balloon stays inflated, what's keeping that balloon inflated? The pressure of the gas. What is pressure in terms of gases? It's just simply the gas molecules bouncing against surfaces, right? And gas molecules can also bounce against liquids. So they don't always just like hit a liquid and dissolve into liquid. They can hit the liquid and bounce off. So you can have a partial pressure of gas above a liquid, and that is just, again, relationship to both temperature as well as the partial pressure is related to the temperature, right? Because the higher the temperature, the faster the molecules are moving, thus the higher the pressure. Now we can think about what this is conceptually. So you've all drinking soda or seltzer at some point in your life. If we think about a closed can of soda, it has high CO2 pressure, thus high CO2 solubility. The can is closed, so it's sealed. You're not losing meaningful amounts of CO2. Thus, you have high CO2 pressure, thus lots of CO2 dissolved in your water. Conversely, when you open the can of soda, you decrease the pressure, i.e. you let some of that CO2 out of the headspace of your soda. What does that do? Well, it decreases the pressure because you have less gas molecules. Thus, it decreases the solubility of CO2. So if you open a can of soda, it's nice and bubbly and awesome, right? Because the CO2 dissolved in that can of soda or seltzer, whatever, carbonated beverage you're drinking, was being held in there by the pressure of CO2 in the headspace above that soda or whatever. When you open a can of soda, that CO2 pressure essentially goes away. Thus, the CO2 is not being held into the liquid as it should be, and the CO2 starts to physically escape. So when you open a soda and you leave it on the counter for a half hour, it'll become less bubbly over time because there's less CO2 holding that CO2 to be dissolved inside your liquid. Now, if you leave that soda can long enough, it's going to go completely flat, i.e., there's no meaningful amounts of CO2 left dissolved in your can of soda. Thus, you probably just throw away your can of soda because flat Coke tastes awful. I don't care what anyone says, flat Coke is awful. That's the idea conceptually, right? Gas can exert pressure. You guys know this from your, when we worked in the lab and our gas laws lectures, right? Gas exerts pressure. And so this leads us to concentration. Now, we can calculate the concentration of something. Now, concentration simply refers to how much solute is dissolved in a given volume of a solution. That's all. So if I have 50, if I have 50 grams of sugar in 1 liter of water, my concentration is 50 grams per liter. That's all it really is. So, but we do have some special terms. We have this, and you might have seen this before. It's a weight divided by volume percentages. So we typically call this weight to volume, i.e. W divided by V percentage. So this is the number of grams of a solute dissolved in 100 milliliters of a solution. So if you say 50% weight to volume, that means there's 50%, 50, your math ends up breaking down as this comes out to 50, right? So that was a bad way of explaining, but we'll get to some math in a second. That'll be much more clear how to explain this. So this is our weight to volume percentage. How much weight do we have dissolved in a given amount of a solution? So for example, vinegar itself contains 5 grams of acetic acid, which is gross, in 100 milliliters of a solution. So our weight to volume percentage concentration is 5 grams divided by 100 milliliters times 100%, thus giving us 5% weight to volume. Now, I want to make mention about one thing. We are comparing grams to milliliters here. Those are equivalent terms on the metric scale. If we had 5 kilograms, we'd have to convert this 100 milliliters into into liters, right? Right, so they have to be equivalent units, right? Grams and milliliters are equivalent, kilograms and liters are equivalent, milligrams and milliliters, right? I mean, so on and so forth. So just have to make sure that when you're doing this math, this weight to volume, that they are working on equivalent units. Grams and milliliters are equivalent units. All right, so we can also look at volume to volume percent concentration. So if we're not physically dissolving a solid in a liquid, if we're trying to dissolve a liquid in a liquid, it's the same thing. Volume to volume gives us volume of a solute divided by the volume of a solution times 100%. So for example, if we have a bottle of rubbing alcohol contains 70 milliliters of propanol, which is just the alcohol, anything that ends in OL is an alcohol, just as a note, into 100 milliliters of a solution, then the volume percentage is going to be 70 milliliters of propanol divided by 100 milliliters of rubbing alcohol, giving us 0.7 times 100, giving us 70%. Now, if you've ever wondered when you go to the, say the pharmacy and you buy, rubbing alcohol, that's 70% isopropanol or 70% ethanol. That 70% comes from this volume to volume percentage. What does that mean? Well, when you buy 70% rubbing alcohol, it's 70% rubbing alcohol and 30% water. Because what it ends up working out is 70 milliliters of rubbing alcohol divided by 100 milliliters of water. So just as a note, giving us 70%. So just as a note, that's if you ever wondered why, you could buy 70% alcohol and what it means, this is what it means. So let's do a problem with this concentration units. So we have weight to volume and volume to volume. That's pretty much all we're really going to do in terms of these percentages. But our problem we're going to do is a saline solution used in intravenous drips contains 0.92% volume to weight sodium chloride in our buddy water. How many grams of sodium chloride are contained in a 250 milliliters of this solution? Well, as we always do with these problems together, identify the known quantities and the desired quantities. Our known quantity is 0.92% weight to volume of sodium chloride, and we know we're injecting, or so we know we have 250 milliliters. That's what we know. We want to know how many grams of sodium chloride are contained in that 250 milliliters. Well, we have to do some conversions, right? So our conversion we know from our weight to volume, equation we talked about previously. We have to write it out as 100 milliliters of solution contain this much sodium chloride, or there's this much sodium chloride in 100 milliliters of solution. Now we're going to choose the one on the right side here because we started off with 250 milliliters. We want to cancel milliliters out because we want grams. So we'll use this conversion factor. And all we need to do is multiply our total volume times this problem, right? 0.92 grams per 100 milliliters. Now, our final answer gets 2.3 grams of sodium chloride, but how did I get that 0.92 over 100? Well, just remember back to our math here, right? Mass of a solute divided by volume, right? And our volume is always 100 milliliters here. That's all. So to get 0.92, well, I need X amount, right? 0.92%, I need X amount. That X amount is going to be 0.92 grams. So, yeah, so you can easily go from, this 0.92% to grams just by simply using 0.92 as your grams, right? Because it's always divided by 100. So just as a note. And so this is what we get. We choose a conversion factor. Based upon that equation, we solve the problem. We get 2.3 grams of sodium chloride in our 250 milliliter solution. Because remember, it would be 0.92 grams in 100 milliliters, 2.5 times 0.92 is going to give us 2.3. Just conceptually going through our friend math. Fun stuff. So a very important type of concentration unit. Now, weight to volume is very important for science, but one of the most sort of pressing issues of our time is climate change. And we often hear climate change discussed in CO2 in parts per million. Well, what does parts per million really mean? Well, when a solution contains a very small concentration of a solute, it is often expressed in parts per million, i.e., as of last year, CO2 is at concentration in the atmosphere of 411.29 parts per million. What does that mean? Well, parts per million is expressed as one of two things. The mass of a solute in grams divided the mass of a solution in grams times 10 to the 6, so million, or volume of a solute in milliliters divided by the volume of the solution times 10 to the 6, again, millions. So that's what's parts per million. How many parts do we have per million of a given solution? That's all. So it's small units, but in the case of something like climate change, parts per million is a big unit, right? In terms of like, if you think about what happens, or actually what's still happening in Flint, Michigan, right, with the lead in their water, they have parts per billion concentrations of lead, and that's enough to be very, very dangerous. So small concentrations can be meaningfully important. So I don't want you to think that even though parts per million is small, that it's not a meaningful amount. It can be. It just depends on what you're working with. Now, parts per million of sugar, not very much, but parts per million of CO2 in the atmosphere, that's a lot of CO2. Just as a note. So that's parts per million. Just wanted to bring that one up. Now, the more important one for today, weight per volume and volume per volume is important, but arguably the most important concentration units we'll talk about is molarity. Now, molarity simply refers to the number of moles of a solute per 1 liter of a solution. Now, we get this abbreviation as big M, as in molarity. And so I don't want you to get confused with moles, which we write as MOL. We're thinking about molarity, big M as in moles. So again, we have moles, MOL, not molarity, two distinct things. Molarity is divided by how many moles in 1 liter of a solution. So let's talk about how we use this. Now, we're going to calculate the molarity of a solution made from dissolving 20 grams of sodium hydroxide into 200 milliliters of a solution. It doesn't matter what the solution is, we'll pretend it's water. So that's what we're trying to do. Taking an amount of sodium hydroxide and dissolving it in an exact amount of a solution. So we need to do, as always, identify what we know and identify what we need to know. So we know that we have 20 grams of sodium hydroxide, and we know we have 250 milliliters of a solution. We want to know our desired quantity, which is mole per liter, or the molarity. So how do we go about doing this? Well, we first convert the number of grams of a solute to the number of moles, and then we convert the volume to liters if necessary. Now, remember from this equation, it's always in liters. We're working moles per liter. So we have to always be working in liters. Now, this problem I gave you is in milliliters, so we have to convert milliliters first to our friend liters. So the first thing we're going to do is use the molar mass to convert grams of sodium hydroxide into moles of sodium hydroxide. So we head over to the periodic table. The molar mass of sodium hydroxide is 40 grams per mole. So you sum the 16 plus 1 plus 23, which gives you 40. So that's how we get the molar mass of sodium hydroxide, something we talked about a few classes ago at this point. So we have 1 mole of sodium hydroxide has 40 grams, right? That's how we express that. So we multiply this conversion factor, 20 grams of sodium hydroxide, multiplied by 1 mole of sodium hydroxide contains 40 grams, which cancels our grams out, leaving us with 20 times 1 divided by 40, giving us 0.5 moles of sodium hydroxide. Okay, so that's how much we're dissolving, 0.5 moles, but that doesn't quite help us. Now, we need to calculate molarity because we're only dissolving it in a specific amount. So that's the first step. We figure out how many moles of sodium hydroxide we have. Again, just finding the molar mass, 1 mole is 40 grams. Thus, we can use that to calculate how many moles of sodium hydroxide we have. Next, we take that volume, 250 milliliters, and we multiply it by a conversion factor. So we know that in 1 liter, there is 1,000 milliliters. So that's our conversion factor. Milliliters cancel, thus giving us 0.25 liters of a solution. Now, we just put all these things together. We know molarity is equal to M, which is equal to the moles of a solute, which we calculated to be 0.5, divided by the liters of a solution, which we calculated to be 0.2, giving us a total of 2 moles, or 2 molarity units, right? Moles per liter. So again, it's a sort of a piecewise way of doing things, but again, we started off with this is how much mass in this liquid. We want to know how many moles per liter. And we simply just have to convert to what we know, right? We need to convert to how many moles are in 20 grams of sodium hydroxide and how many liters are in 250 milliliters. Once we have that information, remember the equation is moles per liter. Once we have those two pieces of information, we divide the moles by the liter, giving us the molarity, i.e. 2 molarity, 2 moles per liter. So that's the concentration in terms of molarity. When we dissolve, again, 20 grams into 250 milliliters of solution. So now, molarity is also a conversion factor, and this relates the number of moles of a solute to the volume of a solution it physically occupies. Now, to calculate the moles of a solute, we rearrange the equation for molarity. So we had molarity, big M, equal to moles divided by volume. We can rearrange that equation to express it as moles of a solute equals molarity times volume in liters. So That's one way we can rearrange the equation. Or we can calculate the volume of a solution by rearranging the equation for molarity. Volume in liters is equal to the moles of a solute divided by molarity. So again, we're just taking this equation and algebraically mixing it up to calculate either moles or volume when we know molarity and volume, or when we know molarity and the number of moles that we have. So let's just give an example of this to show you what I mean by this. So the question we're going to try to answer is what volume in milliliters of a 0.3 molar solution of glucose contains 2.5 moles of glucose? So what do we want to know? Well, we just want to know the volume, right? That's all we want to know here. V. What do we know? We know we have 0.3 molarity, because that's what it told us here. And we know we have 0.25 moles of glucose. So based upon this previous slide, which one can we use? Well, we can use this bottom equation. We want to know volume, we know moles, we know molarity. So we just stick everything into that equation, provided it's in the right units. Our volume is going to be in liters. We have moles in molarity, so everything is in the right units. So we simply just use this equation and divide 0.25 moles of glucose divided by 0.3 moles per liter of this glucose solution, giving us 0.083 liters of a given solution. So nothing crazy, right? Now we can then use, just as a note, this is the volume is in milliliters, so we're going to go a little bit further because our answer was originally in liters, right? Because this is moles per liter. So we had our answer in 0.83 liters. Now we want to convert that 0.83 liters to milliliters. Now we know that there's 1,000 milliliters per liter, or in 1 liter there's 1,000 milliliters. We choose this conversion factor. So we basically multiply 1,000 by 0.83 liters, giving us 83 milliliters for our answer. So again, we can use that equation, moles divided by liter, gives us our molarity. We can mix that equation up 3 distinct ways to calculate an unknown given a problem. So fun, nothing super complex, but really kind of handy, for calculating molarity and other things. Now, my favorite type of math associated with this is actually dilutions. I really enjoy this type of math. I used to do it a lot, and you do a lot in science laboratories. But a dilution itself is the addition of a solvent to decrease the concentration of a solute. So the solution volume changes, but the amount of solute, i.e. what you're dissolving, does not change. So think about it this way. If we have a solution that has, say, salt dissolved in water, we can dilute that solute by adding more solvent. So we can dilute our salt by adding more water. So you see that we start off with what 10 blue balls here in some volume of water. We add more water and we still have the same 10 blue balls, but we have more volume. So we get new values here. So we have some molarity and some volume, and so they have to equal our final value. So M1V1 has to equal M2V2. So it's kind of like our gas laws, right? Where they have to be proportional to both sides. Our original concentration has to be equal to our final concentration because we're not changing anything in the system. All we're doing is increasing the water. So if we're increasing the water, thus our molarity has to physically drop. So let's conceptually use M1V1 equals M2V2. Let's conceptually use this. Now, what is the concentration of a solution formed by diluting 5 milliliters of 3.2 milliliter glucose solution to 40 milliliters? So conceptually, we're starting off with 5 milliliters, and in that 5 milliliters, there's 3.2 moles of glucose, or so 3.2 molarity of glucose. We're taking that 5 milliliter solution and adding 35 milliliters of water, thus increasing the total volume to 40 milliliters. So what we want to know is the final concentration of glucose in this solution. We're looking for M2 in our equation, right? M1, V1, M2, V2. We're looking for M2 here because we know V2. So we start off by knowing V1, which is 5 milliliters. We know M1, which is 3.2 molarity. And we know V2, which is 4.40 milliliters. We're looking for M2. So we set up an equation, right? M1 V1 equals M2 V2. And we want to isolate M2 on one side, and we do that algebraically by dividing both sides by V2. So if we divide this side by V2 and this side by V2, V2 cancels out on this side, leaving us M1 times V1 divided by V2 equals M2. Right? We just rearrange this equation. And you can rearrange this equation any way you potentially need. But mathematically, we solve this problem. M2 equals M1 divided by V1 divided by V2. We have 3.2 M, 5 milliliters, 4 milliliters. The milliliters cancel out, giving us this mathematic expression. So 3.2 times 5 divided by 40, giving us a final concentration, M2, of 0.4 molarity. So that's kind of a handy thing to use, right? M1 V1 equals M2 V2. You can also express that as C1, so concentration 1 times volume 1 equals concentration 2 times volume 2. So C1 V1 equals C2 V2. But most commonly in chemistry, it's M1 V1 equals M2 V2. So again, one of my favorite types of maths surrounding solutions. I think this is kind of a fun math problem to do. Because conceptually, it's, if you're just diluting something, you're just increasing the volume. But the amount of stuff you've dissolved in doesn't change, right? So you have to decrease the concentration. So I think conceptually, it sort of nicely fits. So sort of heading towards the end of today's class, we have colligative properties. I believe that's how you say it. I'm terrible at pronouncing things. For those of you that are taking biology with me, you know I'm terrible at pronouncing things. But colligative properties are properties of a solution that depend on the concentration of the solute, but not its identity. So conceptually, what we can interpret this as the number of dissolved solute particles affects the properties of the solution, but the identity of the solute physically does not. What does that mean? Well, colligative properties include the elevation of a boiling point, the lowering of the melting point, and the changing of the pressure due to osmosis. So, thinking about this, if you take a lot of salt, you dissolve it in water, you're not changing anything meaningfully, but you do change the boiling point of that water, right? So that's intuitive. Sorry. My bad. So that's intuitively what we're thinking about here, right? You're dissolving something into something that changes the property of that solution in general. So blanketed under colligative properties, we have a volatile solute, and this is something that readily escapes into the vapor phase, i.e. readily escapes into a gaseous form. A non-volatile solute does not readily escape, so it has a negligible vapor pressure at a given temperature. So when I was preparing the acids for 2 weeks ago's labs, so when you guys are playing with different concentrations of hydrochloric acid, I had to dissolve really concentrated hydrochloric acid into water. Now, hydrochloric acid is a very volatile solute. Thus, when you dissolve it in water, it produces chlorine vapor because it's very volatile. That's in contrast as when you dissolve sugar in water. Sugar dissolving in water doesn't produce any gases or anything like that. Thus, it is a non-volatile solute. And as we've sort of mentioned a few times, the vapor pressure above a solution of a non-volatile solute is lower than the vapor pressure of the pure solvent. Well, we haven't mentioned that before, but we've mentioned this idea of vapor pressure or gaseous pressure before. Now, as we've mentioned, colligative properties include boiling point elevation. So a liquid solution that contains a non-volatile solute has a higher boiling point than the solvent alone. So the amount of that boiling point increase depends only on the number of dissolved particles. So as you increase the amount of stuff you're dissolving in a solution, it increases the boiling point. So as you add more and more salt to water, it increases the boiling point of the water and salt solution. So the idea being is that 1 mole of any non-volatile solute raises the boiling point of 1 kilogram of water to the same amount, which is 0.51 degrees centigrade. So every time you add 1 mole of salt to your water, it increases the boiling point of your water by 0.51 degrees centigrade. So not a huge amount, but it does change a little bit. So what you can take away from this is adding salt to your water doesn't meaningfully change the boiling point of the water. It does a little bit, but not really at all. In addition, we can also look at freezing point depression. So when a liquid solution that contains a non-volatile solute has a lower freezing point than the solvent alone. Now, the amount of freezing point depression depends only on the number of dissolved particles, same as increasing the boiling point. And so 1 mole of any non-volatile solute lowers the freezing point of 1 kilogram of water by the same amount, which is 1.8 degrees C. So when you add antifreeze to your car, what is that doing? Well, antifreeze is a non-volatile solute. It dissolves in water, thus lowering the freezing point of your water by 1.8 degrees C per every mole of antifreeze that you add to your water. Pretty fun, right? So some real life things here. Sort of the final thing we'll discuss together, right? I think it's the final thing, if I'm not mistaken, is osmosis and dialysis. Now, the membrane that surrounds all living cells, so your cellular membrane, and for those of you that have taken biology, you know this, but it's semi-permeable. And what that means, it allows water and small molecules to pass, but blocks the passages of large molecules and ions. Now, osmosis specifically describes the passage of a solvent, water, principally water. Osmosis almost universally always refers to the movement of water. Osmosis describes the movement of a solvent across a semi-permeable membrane from a solution of low solute concentration to a solution of high solute concentration. Now, conceptually, what does that look like? Now, if we have this membrane, we have water with nothing dissolved in it and water with something dissolved in it. Osmosis tells us that water moves from this side where there's nothing dissolved to this side where there is stuff dissolved. So that's what osmosis is. Now, remember, this is in contrast to diffusion, right? When we talked about diffusion, diffusion tells us that we have high concentrations of the solute. Diffusion tells us that the solute should move from this side to this side until they are in equilibrium on both sides. But osmosis is the exact opposite, but it describes how water moves from low concentrations to high concentrations of solute. Which leads us to a term which we call osmotic pressure. And osmotic pressure, and you might see this in your average everyday life, like you'll see osmotic pressure of like filters and stuff like that. But this is the pressure that prevents the flow of additional solvent into a solution on one side of a semi-permeable membrane. So, more terms. Now, two solutions that have the same, and so let me just actually take a step back. So osmotic pressure prevents the flowing of solvents into the solution on one side. So it keeps the solute essentially balanced in terms of its concentration. Now, so for two solutions with the same osmotic pressure, they are said to be isotonic, i.e. there's no net movement of water. Because remember, water moves from this side to this side. Because there's not equal osmotic pressures here, water flows from this side. If there was equal osmotic pressure, water would not flow net, right? So I wouldn't gain water on this side or gain water on this side if the concentration of solute was equal, i.e. the osmotic pressure is equal. So thinking about your body, solutions that are isotonic with your body include 5% weight to volume glucose and 0.92% weight to volume sodium chloride. So when you go, if you've ever been to the hospital and you've got an IV drip, they give you 0.92 weight to volume sodium chloride, typically speaking. And they do that because this is isotonic with your body, i.e. it's not going to cause any net movement of water in and out of your cells. Now, a hypotonic solution has a lower osmotic pressure than the bodily fluids. What that means conceptually is that there's a lower concentration outside your cells than there is inside of your cells in terms of something dissolved. So you can think of this maybe like there's less calcium on the outside than there is calcium on the inside. And so that creates a hypotonic solution where there's a deficit of whatever your cells are or whatever your thing is inside, right? There's less in solution than there is inside. What this does is it causes water to diffuse into the cell. And now, conceptually speaking, if you're having water rush into your cells, it causes the cells to swell and eventually rupture. Now, that rupturing of cells, if it's talking about red blood cells, is what we call hemolysis, or some people call it hemolysis, but hemolysis, which is the rupturing of red blood cells. And the final one is when we have a hypertonic solution, where there's higher concentrations inside the solution than there is inside your cells. So what this causes, a difference in osmotic pressure, high osmotic pressure here, low osmotic pressure here. And what this does is causes a net movement of liquids from inside your cells moving into outside of your cells. So it causes water to diffuse outside of your cells, so it causes your cells to shrink. Now, this process of your cell shrinking is called crenation. Not a very common term you hear, but it's called crenation. Again, causing your cells to shrink up and shrivel, basically dry out, right? And your cells can actually dry out in a liquid solution. It's kind of weird to think about, but osmosis can cause things to dry out even in a liquid solution. This brings us to dialysis, and I figured we'd talk about this because a lot of you guys are interested in medicine. Now, in the human body, as you guys probably know, liquids are filtered and bloods are filtered through the kidneys by the process of dialysis. Now, we can artificially create dialysis machines that do the filtering that kidneys will typically do if a person's kidneys have failed. So in dialysis, water, small molecules, and ions physically can pass through a semi-permeable or dialysizing membrane, and only large biological molecules like proteins and starch physically cannot. So this allows your body or a machine to filter out waste products like urea and other large molecules to eliminate them in urine. So that's what dialysis is conceptually in your body. But when we think about dialysis, we're typically thinking about when a person is incapable of removing waste products from their blood, i.e. their kidneys have shut down partially or completely. So dialysis is you have an artery and a vein, and you essentially pump blood out of an artery. Arteries take blood away from your heart, just as a note. They pump blood out of an artery into a machine. They pass it through dialysis tubing, which removes urea and other bad chemicals. And that gets removed completely. And then it pumps the blood back into your veins, thus returning it back into your body. So we can use colligative properties of dialysis to physically remove toxins from your blood, i.e. doing what your kidneys do, but with an artificial instrument. So that's dialysis. If you ever wonder how dialysis works or how your kidneys work, that's how your kidneys actually physically work. So that is going to be the end of today's class. So I'm going to stop recording.